Well, good evening, everyone, and welcome to is this the fourth or the fifth Galloway Glens event in our Natural Sciences series? Some well-kent faces in the waiting room I can see, plus some strangers. So welcome to Galloway Glens, and welcome to this event. But tonight's event is all about salmon and trout and the amazing migrations they make. In the chat room, we've got Jamie Ribbons from Galloway Fisheries Trust and Mark Bilsby from the Atlantic Salmon Trust, who are going to try and answer many of the questions in there. I'd also like to remind you we've got many more events coming up. So if you check our Facebook page and our website, you'll see in 2 weeks' time we've got willow tits, which is all about the desperate state that willow tits are in at the moment, with one of the fastest declining small bird species in Britain, largely because the habitat is probably too tidy. So maybe teenage boys should be left to look after woodland, and then we'd have more willow tits. So tonight's presentations, we'll start off with two presentations on a traditional format, and then we're going to change about a little bit, and we're going to go to a little debate between Dr. Sam Beck and Professor Ken Whelan and myself. And at that point, my colleague McNabb Laurie will take over filtering questions to us. So, without further ado, Ken Whelan is just going to start sharing his screen now. And Professor Ken Whelan is the first presenter. Now, he's, to anyone in the fishery world, he doesn't really need any introduction. He's one of the foremost fishery scientists of the last 30 years. He's the research director for Atlantic Salmon Trust and has at least 100 papers to his own name and contributed to many, many more. He's one of the most well-kent fisheries guys currently operating. So, Ken, over to you.
Thank you very much indeed, Nick, and good evening, everybody. First of all, just to thank Nick and everybody in Galloway Glens for inviting me this evening. It's great to be with you all. And we're going to talk a little bit about fish migration. I want to be, at the beginning of the talk at least, I really just want to get us all thinking a little bit and to be a little bit provocative in terms of trying to think about why fish migrate and why has this adaptation, this migration, why has it come about? And then we'll speak at the very end a little bit about how successful it is in terms of fish adopting this and staying with it, if you like, in terms of the actual migration pathways and so on. But I think it's always important to go back, if we can, into the ice and back into the past and have a little think about how these things emerged. And certainly some of you may be surprised to know that the original of the species, the original of the salmon race, if you like, was probably around 40 million years ago in the Eocene. That's a hell of a long time ago, I know, but it is interesting that they've been around in one form or another for all those years. But the fossil record and indeed more recent molecular data indicates quite clearly that in terms of separating them out into salmon as we know them, into the Atlantic salmon and then into the various Pacific salmons, that probably happened again a huge long period of time ago, about 15 or 20 million years ago. And it probably came about perhaps following a cooling of the Arctic Ocean that was about at that stage, or at least the beginnings of the Arctic Ocean. So what we had then was we had the Atlantic salmon, and the Atlantic salmon gave rise to all of the Pacific species. But at that stage, the 15 or 20 million years ago time period, we could clearly differentiate then between Atlantic salmon and the Pacifics. But let's jump forward then in time and let's talk a little bit then about what we call the Ice Age, which in reality is just the most recent Ice Age as such. And we always think about that in the context of 10 or 12 or 15,000 years ago. And even that seems a good distance from now. But in reality, the most recent ice stage stretched from about 27,000 years ago. And in reality, the Ice Age itself then probably ended somewhere between 8 and 12,000 years ago. Certainly when I was in school, any of the maps that we saw in the classroom, it was always very convenient in the sense that there was always little bits of territory that were left free of ice. So whether it was the edge of the south of Ireland, whether it was part of Wales, there were all these little refugia, and that made it very easy for the teacher in terms of being able to explain to you, well, there was always a little bit left without any ice, and that's where everything came from. And we know now that that just isn't true. In reality, at the peak of the last ice age, the last ice event, all of Britain and Ireland was actually covered in ice. And the reason we know about this is by looking at the remains that we find in the coastal areas off the west coast of Ireland and Scotland. So along the continental shelf to the west of Scotland and Ireland, remnants of these glacial moraines are masses of rocks and sediment that are carried down and deposited by the glacier. So remnants of these glacial moraines have been found. There's been eskers, which are these lovely rims of gravel that you can see on land as well. There's also meltwater channels. So all of this clearly indicates that these massive big ice mountains were moving around on the bed of what we now call the sea. And the other thing to remember is that each major retreat of the ice was actually accompanied by a re-entrenchment. So it wasn't that the ice melted. The ice melted in part, then it refroze, froze hard, slightly melted. So it was all change. It was a massive amount of change is really what was happening. But the retreat of the ice from the continental shelf edge, it began about 26,000 years ago. And this was about 1,000 years after the last glacial maximum. You'll remember I mentioned 27,000 years ago in the earlier slide. So it was at its peak about 27,000 years ago, 26,000 years ago, it all started to happen. And the ice sheet began to retreat from the southern extremities in the Scilly Isles, for example, at 23 to 20,000 years ago, while it was not until 19,000 to 15,000 years ago before it began to retreat along the eastern English coastline. But there's now clear evidence that there were massive paleo flow events around this time. And these paleo flows actually have me fascinated because they do tend to explain a lot of the mystery in terms of how our freshwater fish and how our invertebrates and so on, how did they get back into these islands if in fact they were covered in ice? And we know from the evidence that is now being collected, there were massive movements of fresh water. And these often occurred contiguous with the ice sheets. And these massive paleo flows were more than an order of magnitude greater than present day flood events or flood peaks. And they were very often characterized, and this is going to sound very familiar, they were characterized by milder periods of the post-glacial epoch, you know, what we would call now, you know, climate change events. Such big flood peaks, the most recent of which we know to have occurred between 25,000 and 17,000 years ago, were caused by a combination of climatic factors, such as high rainfall, glacial outwash, snowmelt, and the melting of permafrost. So we have evidence for those. But I would ask, in terms then of more recent times, have we any evidence of a large amount of fresh water being around? And really we do, because trapped between the southeast and southwest land bridges, the ice sheet in the north was holding all this in. And what we had then is a situation where the Irish Sea was a massive freshwater lake. In addition to that, in the North Sea, there's also evidence that there was an equally large, if not larger, glacial lake. So the point I'm making with all of this talk about ice and about fresh water is the fact that there was a huge amount of dilution going on. The seas that were around at that time may have been far more dilute than anything that we would consider a sea at the moment. And salmon may very well have evolved, taking advantage of these dilute seas. And perhaps even, and this is just really speculation, as I say, but perhaps they were like herring, and perhaps they spawned in the marine gravels, because in reality, they were in very brackish water. But the retreat of the ice then, if you think about it, glacial streams began to form. And as the glacial streams began to form, in the bed of the glacial streams, you had clean, fresh gravel. Perhaps they offered a safe haven for the young of these salmon as they evolved. And perhaps there was a selection advantage in terms of the fish choosing these particular locations. So again, just think about this. We regard constantly the streams in which the fish are born and where they live. We regard those as the salmon's home. But some years ago, I was working in Greenland, and part of my work, I had to actually do a lot of dissection of fish and take samples and so on. And I worked in the local fish factory. And I was very fortunate to make friends with the assistant manager of the fish factory. And he happened to be a very, very good Danish biologist. And he was explaining to me one evening very late as we were taking samples that he always went out and caught about 12 or 14 feeding Atlantic salmon off the coast of Greenland as a subsistence dish, if you like, that he kept in the freezer for himself and his family. And he said he was always very interested at the behavior of the fish as they arrived into the local bays and just off the coast where he lived. And then he said the most extraordinary thing to me. He said these fish really are very, very exact in terms of when they arrive. And sometimes, he said to me, they arrive when there's very little of their traditional food about. And he said they have to go then feeding on a wide variety of different food organisms. And this was a revelation to me. If the fish were arriving before the fodder fish, the fish were then being driven to arrive at a particular point in terms of their life cycle. Perhaps, just perhaps, Greenland, and indeed, as we'll see later, the northwest coast of Norway, where the grilse feed, perhaps that's home. Maybe the migrating fish are actually going back home when they go to the area where they feed. And perhaps the location where they're laying their eggs is exactly that. It's a location to keep the eggs very safe and very sound. So this is just a very rough map of Greenland, just to put it in perspective for you. So a lot of the bigger salmon from Scotland and from Ireland, they feed in this area here off the southwest and the west coast of Greenland. So the area I was working in is a little town here called Cockertock. The distances that the fish travel are extraordinary. This ability to be able to migrate these distances at relatively small sizes is really awe-inspiring. So for example, the mouth of the Dee to grilse feeding grounds off the northwest, indeed, Norwegian coast, it's about 1,500 kilometers. But from the little town that I was working on here in Cockertock, back to the mouth of the Dee is about 3,000 kilometers. So these fish are making these extraordinary journeys. So when does this pattern of migration begin to actually to be revealed in the life of the salmon? At the time when the reds, as we have at the moment in terms of this kind of March, April time, when the reds are still full of these little olivants struggling to come to the surface and begin to feed, as they begin to feed and as they develop into fry, it's a very, very crowded area. And at this point, there's absolutely no sign of a migratory behavior. These fish are showing no great wish to start moving. They are certainly moved a certain distance as a result of competition, but they're not actually on a migration at any point that we're aware of. But as they get bigger, and most of our smolts in Scotland are 2-year-old smolts, and about 6 to 10 weeks before they actually go to sea, they begin then to imprint the actual taste of the water into their brain. And if you think of it like the layers and layers and layers going on to a cake. So the first layer that's laid down is the layer of taste that's closest to the location where they were spawned. And as they move downstream, these pathways, chemical pathways, are actually then imprinted on the brain as the fish moves down towards the estuary. And as the fish begins to make this move towards the estuary, you'll notice that they begin to jump. And people often say, well, it's spring and they're jumping for joy. Well, nothing could be further from the truth. These fish are actually incredibly uncomfortable because their physiology is changing. Their body is telling them you should be in salt water. And you'll see these fish tossing and jumping on their way to the ocean. But they're being driven. They're being driven downstream and driven towards the ocean. And once they get into the ocean, and remember the distances I was talking about, thousands of kilometers, we know now from the tracking work that Sam will be talking about, we know from earlier tracking work that these fish move very fast through the bays, and they move very fast along the nearshore areas. And they need to migrate from the river mouth to their feeding grounds quite quickly. So they need to move from Scotland initially up to this area here off the northwest coast of Norway. And they need to be there, but ideally by about mid-July. And they feed in that location then from mid-July right into early winter. So if they're going to get to that particular location, what's driving them? I have an animation now that I'm going to show you that will give you at least an idea of what may be happening. So when they're moving into those locations and across the sea, is it just the currents that are driving them there? Are they following perhaps the smell of the adult salmon? Are they following electromagnetic cues that they find in the ocean? What we do know now is that these smaller smolts, which generally will be between 12 and 15 centimeters, very tiny little creatures, when they go out to sea and they're in these huge great currents, there's not a lot they can do about moving voluntarily to the area where they're going to feed. They're generally taken by the current. They can certainly feed within the current and they can move within the current. And we do know that there are certain locations in their journey northwestward, or northeastwards rather, we do know there are certain points where they do switch currents. So there is a directional component. They are certainly going somewhere, but largely in the initial stages, they're being taken by the currents. But once they reach about 750 grams in that period around early winter into winter itself, at about 1.5 pounds, 750 grams, they become masters of that surface layer of the ocean. And then they really can begin to roam. And they can make a decision whether or not they're actually going to come back home or stay at sea. If they're going to come back to the rivers to spawn, well, these fish then generally come down around the Faroe Islands, and then they will overwinter there and then make their way down in early summer back into our rivers. But if the fish, if they're not maturing, and they are then inclined, of course, to stay at sea for maybe another year or maybe another 2 or 3 years, those fish are going to move across then the north of Iceland, we think, in through East Greenland over to West Greenland. So the fish then are constantly making these decisions, and indeed nature is making these decisions for them. So let me then show you this graphic. And this little animation, it was put together by colleagues of mine when we were running the first of the big salmon programs called SALSI. And what it shows is 2 groups of smolts going to sea from Northwest Ireland, from Donegal. And it's what we call a particle model. So it's a simulation of 10,000 smolts leaving Donegal in May time. And what was put into the model then were all of the information that we had at that time in terms of the movement of surface currents and also the sorts of speeds that smolts themselves could actually utilize for prolonged periods of time. But the most important thing to watch out for is to watch out how the dispersion of the fish changes. So in 2002, we had a year class of smolts that went to sea that was particularly successful. And you'll see why that particular year class was so successful. The reason was that that year class was fortunate to have available to it surface currents that made sure that it was in the feeding grounds by mid-July to early August. Whereas in 2008, the winds had actually changed the surface currents. The surface current pattern was very confused. And as you'll see, the actual simulation indicates that smolts may very well have been lost, and certainly were much, much slower to reach the area, the feeding area, up near the Norwegian coast. So again, that will give you an understanding that even though there's a lot of components that are genetic, and there's a lot of components that are inbuilt in the fish in terms of the migration, they're very much influenced by the environment itself. So this is the feeding area I was talking about off the northwest coast of Norway, and then across here is the west coast of Greenland. So basically, our fish are moving up here as post-smolts generally, and then if they decide to come back, they're coming back. Then if they're coming back as grilse, then back to spawn, they will generally overwinter in this area here around the Faroes, and then make their way back then, as I say, in early summer. If they're not maturing and they're going to stay at sea for several more years, this is the sort of pattern they may very well be taking. We don't know the exact routes in terms of this particular journey across to West Greenland, nor do we know much about the routes when they come back. But we do know a good deal now about this initial movement of smolts, and the animation actually shows that. So I'll just run the animation now. So this is 2002. So this is a little bit like a computer game. We're trying to get the fish up here as fast as we possibly can. This is 2008, where the fish actually found it quite difficult and get very dispersed. So if you just watch this for a moment, I'll just let it run. You can see already in June, we have fish already appearing up near where the feeding grounds are. These are very dispersed in this particular one here. So you can see the difference that these surface currents can make. And obviously the fish themselves then will hold in gyres in these areas where the currents will carry on. But in reality, you can see the huge contrast between the successful year and the year when the fish found it far more difficult. I also mentioned that there were key areas in their migration where the little smolts can actually switch currents, because if they didn't switch currents, they wouldn't end up in the feeding areas that they're intending to go to. So these narrows, if you like, in terms of the banding, we know from the work that was done in South Sea that some of the currents, if the fish didn't switch currents, would bring the fish back down in this direction. And yet we have very good proof now that it's in this area here that they generally start their initial feeding. We also know a little bit, and increasingly more, about their preferences. So they tend to prefer areas where the surface temperature is about 9 to 12 degrees. And interestingly, as smolts, they prefer full salinity. They don't actually like any of the diluted areas, any of the areas where there's a lot of fresh water in the sea. They are not the areas that these post-smolts are interested in actually staying in. And that's an interesting contrast because, as I say, these fish, a bit like our sea trout, these fish are really very good at utilizing both full salt and brackish water areas. But again, nature has actually designed it so that the post-smolts themselves are avoiding these more dilute areas as such. So the non-maturing salmon then, as we say, they've left and they've gone over across to Greenland. They're going to stay from 1 to 3 years in Greenland, grow to very large sizes if they stay 3 years, and then back to their spawning rivers. On their way back, we know that it's most likely now that it is electromagnetic cues that the bigger salmon use to get back. Certainly in terms of getting within smelling distance, if you like, of the river of origin along the coast. But the fine tuning is done by smell, or if you want to call it the taste, if you like, of the water. Remember what we were saying about the layers of taste being laid down in the brain? Well, cleverly, as that layering comes into play, the last smell that was laid down is the first smell that the salmon actually, that salmon senses. And as then the fish fine tunes and moves in towards its river of origin, it's obviously then taking away layer after layer after layer of taste or smell. And in terms of the fish themselves, um, there's nothing perfect in nature. And everything is what we call a normal curve. So it's a bell-shaped curve. So there are always 8 to 10% of wild salmon that stray. And in many ways, that's a good thing, because genetically, it's ensuring that there's always some fish that are available to recolonize rivers if the rivers lose their stock completely. So this is not at all a bad thing. And as I say, it's a feature that people often underestimate, just how many of the fish don't actually accurately make it to their river of origin. But what about the future? And the big question is really, in the context of climate change, what's going to happen? We know these fish have been about for millions of years. We know they are absolutely superb at adapting. But the question is, can they adapt quick enough to take account of what is happening as a consequence of climate change? And I think that's really the big question for us. It's not so much whether or not these fish will continue to exist, I think, because I am quite certain they will continue to exist. But will they exist in the locations where we really treasure them? Will they continue to exist in the rivers of southern Europe? Or will they be confined to areas in the Arctic? Will there be a movement again past the coast of Greenland? For example, we know at this stage that there's something like 1,000 kilometers, about 600 miles, between feeding Atlantic salmon in one area of the Northwest Passage and feeding Pacific salmon on the other side of the Northwest Passage. So there are lots and lots of biota at this stage. There's jellyfish and so on that are moving through from the Pacific to the Atlantic. So we may be watching evolution in progress again. And remember how I started. I started by describing salmon eking out a living in these new little streams. These new little streams are beginning to appear in Greenland. There's areas of Greenland that are no longer covered in ice, where these little new rivulets, if you like, of fresh water are certainly attracting in Arctic char at this stage. And who knows, some of the strays may very well start to colonize these locations. So when we talk about the fish adapting, we always assume that the fish are trying to adapt in our location. But really, the big question is whether or not we will lose these fish as a result of these enormous changes that are happening both in the marine environment and in the freshwater environment. Thank you.
Thank you so much, Ken. For those in the meeting who don't know me, I was 25, 30 years working in the fisheries industry, but it's always fresh and new to me, this sort of stuff. Really, really interesting presentation. Got a question from through my thing from an Arthur Eggleton. He was querying that actually, will the salmon move away from the southern range over time of current climate forecasts and just continue moving north? Is the sort of question he's posing.
I think that's a real risk, but there's a few things that we have to remember that, for example, we have salmon that are really well adapted in Spain. And we have the wonderful salmon that are well adapted in the chalk streams of the south of England. So there's lots of variation amongst the salmon. So certainly the stocks that we have, the stocks that are certainly in Scotland, I would be concerned that we could lose those as a consequence of the changes that we're seeing, particularly in terms of the very severe drought conditions, for example, that we saw in 2018. And these changes in the ocean are very, very strange. One example, off the south coast of Ireland at this stage, I'm aware of 4 different species of sea fish that have appeared over the last 25 to 30 years that we didn't have in those areas. For example, gilt-head bream, Mediterranean sea bream. They are now thriving off the south coast of Ireland. So these seas are changing, and they're changing fast.
Thank you. I've got another comment in here about the more on the migration thing. Actually, jumping back is would smell from the land itself be a cue for fish to be homing in on a river. I guess it probably would be one of those senses that are building up on the way out, isn't it?
Yes, I think it is. And certainly uh, it is amazing considering how much work has gone into looking at the olfactory senses of salmon, just how little we actually know about that. But certainly, if you are changing the chemical composition of the river profoundly, it must be, I would think, from first principles, a risk. And certainly one of the reasons why I think we're trying to reduce those pressures, because in a situation where the fish are under such pressure generally, to reduce the man-made pressures is an obvious no-brainer in terms of trying to actually maintain the stocks of salmon.
And the final question before we move on to Sam has come from Mike Wilson. I'm not necessarily going to think you can answer this question because if you could, you'd be getting a significant number of awards. But why are the numbers dropping so significantly in Galloway streams and rivers? My comment on that, and maybe if you agree, is that salmon numbers are highly variable, but on a downwards trajectory over large parts of their range, and it's not specific to Galloway. But there are obviously in local areas specific issues. So I don't know if you want to expand on that.
Yeah, we saw an interesting example of that in terms of the returns that are just coming in now from 2020. Generally, some of our rivers did extraordinarily well in comparison to the last 10 years or so, but there were real exceptions. There were rivers that just did not see that bounce. And certainly, my gut feeling is that it has to do with location in the ocean, as well as the conditions in the river itself. So it's this mix of genetics, conditions in fresh water, conditions in the sea. And I agree with you. I think anybody that can at this stage produce numbers to actually support these particular events would certainly be in line for a Nobel Prize, because it's a very complex area. But certainly through our likely suspects framework in the Atlantic Salmon Trust and the Missing Salmon Alliance, that's exactly what we're trying to do. We're trying to take account of the broad range of issues and put numbers on them and see which we think come out as the most important in terms of explaining these variations that we're seeing in salmon numbers.
Okay, well, thank you, Ken. Carry on asking questions, guys. Ken may have a little look in the chat room himself and maybe answer one or two as we're going forward. But we're next going to move over on to Dr. Sam Beck. Now, Dr. Sam, would you like to start sharing your screen? Now, Sam has recently joined us in this region, working now for Galloway Fisheries Trust. She did a PhD in at University of Iceland and was working up in the University of Highlands and Islands with Professor Eric Vesper. She's come down to this part of the world to help Jamie and his team implement a number of schemes, including a really exciting tagging project that the Galloway Glens is really chuffed to be helping to fund. So, Dr. Sam Beck, would you like to take it away, please?
Yeah, thanks, Nick. And before I begin, I just want to say a big thank you to Galloway Glens to give us this opportunity to talk about the project that we're running here. So I'm going to be talking about the life cycle of the Atlantic salmon and the pressures involved at each of these stages, but specifically focusing on the smolt stage, and then diving into the project, which we'll be kicking off at the end of this month. So migratory freshwater fish are disproportionately threatened compared to other fish groups. So they migrate these thousands of kilometers, like Ken was telling us all about, and they're exposed to numerous different habitats, and each of these habitats have numerous threats associated with them as well. So there's been this world report, comprehensive report of migratory freshwater fish populations and their status globally. So worldwide, there's been a reduction of 76%, or 76% of migratory freshwater fish populations are in a decline globally. And in Europe, this number is higher. So 93% of migratory freshwater fish populations in Europe are declining. So if we look at the indicator, if we look at the distribution of these threats, we can see that in Europe, almost more than 60% of our migratory freshwater fish are threatened from habitat degradation and change. And then if we look at places like Oceania, you can see that there's no climate change listed there. And Australia is part of Oceania. And we know that there's been millions of fish killed due to things like flooding events and droughts, but the data is not yet there. It's not got a bit of data deficit there. And it's the same here in Africa. So we know habitat loss and pollution are also big problems in Africa. So this figure is merely just an indicator of those potential threats. So that begs the question of how can we actually conserve these migratory fishes? So not only do they migrate vast distances and are exposed to numerous habitats, but they also have these really complex life cycles. So this is the Atlantic salmon's life cycle, and I'm not going to go into each stage just yet, but just to highlight the fact there is this freshwater phase and a sea phase. So if we go into the freshwater, they migrate out to sea as smolts, like Ken was telling us about, and then they're at the sea, they migrate to the feeding grounds, have this period of really rapid growth, and then they return to natal streams as adults to spawn once again. I'm going to show you this really cool video from the Ness District Salmon Fisheries Board, which shows salmon spawning in the area. So this is a female here. She tends on her side and she flaps her tail to excavate a redd or a nest. And then behind, you can see males coming along. These are territorial males, and you can see by their beaks, they have these kype here that you can see. And they're very aggressive and will fight over the females. But in the background, you've got these tiny little mature male par. These are sneaker par, and they're or precocious par. And they'll sneak in at the end to try and fertilize some of her eggs as well. As you can see the par coming in, just like hiding away from the males, the larger males, because they can go quite aggressive. And then the female deposits her eggs. And if you look behind her, there's a male coming in, and he'll flutter and release his milt, his sperm, fertilize the eggs externally. And then those sneaker male par will sneak in and also get their way as well. Here they go. So once all's finished, the female will cover up her eggs with these stones and to enable good oxygenation whilst also protecting them from predators. Okay, so as eggs, they're really sensitive. In fact, all early life stages of salmonids are quite sensitive, especially at the egg and embryonic stage. So one of the biggest problems with these early life stages is water quality. So in Galloway, we have particular problems with this, especially with acidification. So we need about a pH between 6 and 9 for the successful recruitment of young. And out with this, there could be serious problems for development. So acidification problems in here are due to the fact of our base pore geology that we have in Dumfries and Galloway. So we have lots of conifer plantations where they act as like your pom-pom does on your bobble hat. It will collect the mist. So the mist is collected on the conifers and they dry. This mist is acidic with all the acidic rain. And when the rain falls, the ground can't buffer the rain and it runs off straight into the streams and the rivers. And then on top of this, you have the areas of peat that have been drained for the forestry. And because they've been drained, they can't absorb that water, also releasing chemical pollutants into the rivers as well, and contributing towards acidification and also towards the release of the mobilization of aluminium, of labile aluminium, which can be very toxic to later stages of the salmonid life cycle. So just to highlight the facts of this relationship between pH and depth. So in the blue line is the pH, and on the red line is depth. So when depth is low, also when there's been less rainfall, there's been an increase in pH, so it becomes less acidic. But then you can see here, rainfalls increase and increase the depth. And when this happens, we get this acid flush, so it comes right down. And then it has this general wave of increasing pH with decreasing depth. And on top of this, we have problems also with siltation. Like eggs are very susceptible for needing lots of oxygen. And if the silt gets run downstream from construction, they can smother the eggs and then have problems with development because they really need good oxygenation, and this can cause high mortalities. And also temperature can actually speed up. If you have higher temperatures, this can actually speed up the rate of development. And if the eggs hatch and the alevins need to start feeding as fry, then the prey, because they've developed too fast, they might not even be available yet. So these are really important factors to consider when thinking about early life stages. And it's the same with the alevins here as well. So the alevins stay underneath the reds for quite a while, and they have these yolk sacs underneath their chins. And then they absorb the yolk sacs using this endogenous nutrition. And then once that starts to deplete, they swim out off their red and they take a big gulp of air from the surface, and that inflates their swim bladder and enables them to be buoyant within the river channel. And then they're known as fry. So here are here's a picture of some fry, the 3 fry and a par. They can remain up to 8 years in fresh water, but that's in populations in northern Quebec. More locally, we have between pars stay in the rivers between 1 and 3 years. So you can see these characteristic par marks here, or thumbprints. So this helps them with the camouflage against the riverbeds to protect them against predators. So we've been doing a lot of work here at GFT for habitat restoration. So this is a river where there is good potential habitat that's there, but there's not very many salmon in this area. So you can see here, it's been really heavily dredged. The rivers are much more straight than they would be naturally. There's conifer plantations on either side, and even some felling that's been going on as well. And also on this side as well, it's just a pure straight dredged river. So what we're trying to do is improve this habitat by planting broadleaf trees around the edges. Not only will this help with preventing against erosion, but also with changing climate, we need to protect our rivers against climate change and shade them against increasing temperatures. So as these trees develop and become bigger, during the summer, they'll protect them against the sun, and in the winter, they'll allow the light into the river, which is important for nutrients. Not only that, but they also will release their branches into the river and provide some good woody debris for the juveniles, which can provide invertebrates and also habitats for them to live in as well. And then you've got the leaf litter from the trees too. So numerous benefits associated with planting broadleaf trees, as well as protecting the banks against erosion. We've also placed these kickers in the streams as well. So this is to encourage the rivers to meander and increase the velocity as well. So rather than having this still water, it also increases that water velocity through and creates habitats as well. We've also been putting some extra boulders in the river to get the habitat looking a bit better too, and more suitable for these juveniles. So then there's this decision of whether a fish should migrate to sea or not. So for females, you've got to think about reproductive success and weigh off this benefit risk scenario. So for a female, the larger she is, the more eggs she can have, or the larger eggs she can have. Whereas smaller females, they can't produce as many eggs. So for them to migrate, so for a female, it's worth the risk to migrate out into the open ocean and be exposed to numerous predators and have to come back to spawn, because she'll produce a lot more eggs and have a higher reproductive success than if she was to stay in the rivers. Males, however, there is there's no difference in reproductive success due to size. In brook trout, at least, is what the evidence is saying. So that suggests that also explains why a large proportion of our par that we see is actually males. In the video that I showed you earlier, this was the case there too. So it's this benefit and cost ratio and getting the balance right. So then if the par decide to go to sea, they need to undergo a process called smoltification, and this involves those of morphological, physiological and behavioural changes. So you can see here, this is a smolt, and they've got this really silver coloration, which enables them to be very camouflaged in the sea when they go out into the open ocean. They have this pelagic lifestyle, and when the sun comes down onto them, that silvery skin will confuse the predators. And also you've got on the dorsal, on the top of the fish, it's much darker. So that also protects them from aerial predators like cormorants or other kind of birds. So as well as internal cues, they've also got these environmental triggers that will trigger smoltification, the smoltification process. So photoperiod or day length is a big one. And then you've also got local river temperatures and local flow conditions as well that will actually trigger downstream migration. So here you've got, it's just important to note that there can be a mismatch between rivers and the actual conditions they experience in the ocean. So the smolts need to arrive in the ocean at a time where there is prey available to them. And if there's a mismatch there, then the smolts could arrive too early or too late and may increase mortality because of it. So in the open ocean, you want to be as big as you can, and then that makes you less available as prey to more predators. So as in you avoid predators more because you're too big to eat. So the bigger you can get, the better. So it's good that it's important to make sure that there's no mismatch between the two environments. So seaward migration of smolts has been found to advance 2.5 days per decade, which is corresponding to changes in the climate. So as the climate warms, the smolts are also adapting the time of their migration to meet this as well. So the status of Atlantic salmon across their range shows quite a big decline since the 1970s. So on the y-axis, you've got nominal catch, and then on the x-axis, you've got the years from 1960 to 2019. And then you've got the different regions as well. So Northern Europe, Southern Europe, North America, and Greenland and Faroes. So this from the 1970s onwards, there's quite a clear decline going on here. And in 2019, it was the lowest ever reported nominal catch since the time series began. And if we focus more on a regional level, you can see in Scotland, there is this clear decline going on. This is a nominal catch as well. And that's in coastal history and in river conditions. You can see a clear decline here too. And then if we zoom in a bit more to that, we're going to look at the reported net catch. And despite the methods, and this is for all age groups of salmon, you can see a decline also from 1970s onwards. And going in a bit more detail, this is the reported rod catch. So here you can see a decline from the 1990s onwards. And this is where the catch and release was started. And the difference between the retained catch and the total catch is the number of salmon released. Again, a decline. And the same for that was for one sea winter salmon or grills. And this is for multi-sea winter salmon. So same graph and the same general pattern of decline. So these trends show that there's been an overall decline in Atlantic salmon across the range, but also especially within Scotland. But their migration remains quite elusive. But what we do know is that the freshwater stage can directly influence the marine phase. So there are numerous pressures in the rivers. So we've got water temperature as a big one. And there's been a Scottish River Temperature Monitoring Network, which has been set up to collect consistent data from around Scotland so that we can use that data to model predictions in how the rivers are going to respond to climate change, and also to identify those rivers that are more likely to suffer from the effects of warming temperatures faster than other rivers. We've got issues with water quality, which I mentioned earlier, hydrology, so these are things like hydropower stations and dredging of rivers, the disruption of the natural hydrology, food supply, so lack of invertebrates, and you've got predators, so human intervention can change the way that predators are naturally distributed. And then you've got things like illegal poaching and barriers, so dams, weirs, culverts, and non-invasive non-native species. So for example, American signal crayfish. So increases in technology such as acoustic telemetry has enabled us to expand our knowledge of smolt migration within rivers and during the early marine phases. So here you can see this is a salmon, and we put a tag in its peritoneum, and then the receivers on the left-hand side here, they're strategically placed along its potential migratory routes. And as the salmon migrates past these receivers, it'll send a ping, and the receiver will record the time, the date, and so that we can see when and which salmon migrated past. So looking into where we are in the southwest of Scotland here, this is Dumfries and Galloway. I'm going to be talking about the River Dee, Cucurbitshire River Dee. This is a catchment that's about 1,000 kilometres in size. And it's also a catchment that has the highest number of pressures associated with it much higher than any other catchment in Dumfries, in the southwest of Scotland. And you can see here all the pressures that I listed earlier is associated with this river catchment, except for illegal poaching, possibly because there's not very many salmon to attract poachers in this area. So we have a fish counter on the bottom of the catchment at the Tongland Fish Pass, and these are just the figures here that over the past 13 years, 10 years. And you can see that in 2007, 2008, about 1,000 salmon were caught. I'm just going to focus on the salmon for the purpose of this presentation. And then over time, it slowly decreases until 2019, where we get 100 adults returning upstream to spawn. But I just want to bring your attention also to the asterisk. So this is just when the vackie was out of action, when the fish counter was out of action. So normally it's only for a few days or a couple of weeks, but in 2018, a new lift pass was installed in the vackie, so it was out of action for the whole year, and also until June in 2019. So these numbers, this 100 salmon that were detected going up the ladder in 2019 might not be as low as we think it is, and with figures from 2020, we can already see that these figures have increased, but overall these numbers are much lower than they should be. So this is where the fish counter is based, at the bottom of the catchment on Tongland hydropower. So this is a hydro scheme, one of the first large hydro schemes in Scotland, and it goes right up the river catchment. I'm just going to be focusing on the main stem. So you've got this one at the bottom, the fish migrate through the fish pass up here, and then they have Loch Hen, which is a really long, thin loch that they need to migrate through. And then they get to the bottom of Ilston Loch, fish pass, and then the bottom of Carlsbad, fish pass, and then they hit Ken Dune. This is an impassable dam, so the fish can only migrate up to this point here. So just to show you what the fish pass looks like, so the Atlantic salmon the adults will migrate up, come around, and then they have this fish ladder where they jump up each step, and each step has like a resting area for the salmon to gather themselves before continuing on, and again up here as well. And that's a similar fish pass at each of these hydro stations. So you got these fish passes were designed thinking about upstream migration mainly, but what about downstream migration? So we know that smolts utilize the water flow, they follow the highest water velocities, and when those turbines are generating, the higher water flows are actually straight through the turbines. So this can cause a lot of mortality during the downstream migration. But also we've got problems with standing waters. So a recent study shows that up to 55% of smolts fail to migrate through the standing water. And then you've got predation associated with this change in hydrology due to either hydro schemes or just human intervention in general, with predators accumulating maybe where they historically once were not. And then, so just to give you the aim of the project, so we want to understand the migration patterns and success of smolts to the River Dee in Cuckoobershire. I mean, the questions we want to ask are, where are mortalities the highest? How many smolts are successful in reaching the estuary? And do standing waters and/or hydropower stations influence migration? So for the project design, we aim to catch about 50 smolts, to tag them, and each of these traps we check daily. So the methods we'll be using to catch them are the rotary screw trap, which is here. These screws will increase the water velocity and draw the fish through, the salmon, the smolts through, to be stored in the landing net here, and pike nets also. And then we'll also place 15 receivers down the river catchment south of Carlsbad Loch all the way through to the estuary. And these will be deployed between April and July. So to summarise, numbers of Atlantic salmon are in the decline. There are less than 100 adults that were recorded returning to spawn in the Cuckoobershire River Dee in 2019, but numbers in 2020 have improved, but overall are still lower than it should be. There's this critical window of migration for smolts, and any disruption of environmental cues may cause mismatches between the environment and the physiological processes. So that could be things like rapid temperature and precipitation changes, which are occurring, and also hydrological changes as well. But advances in technology are enabling us to better understand these patterns of migration and identify areas of concern. But Atlantic salmon have very time-consuming and lengthy migrations, and numerous factors are acting over broad geographic scales. But it's just important to note that relative to other catchments in the local area, the Kubrusha D has much lower numbers than in comparison, which suggests that there's something happening locally within the catchment itself, as well as in broad other geographic scales as well, the larger geographic scale. So to keep updated with how this project goes, you can follow us on Facebook, Twitter, Instagram, and also we'll be posting some updates on the Galloway Fisheries Trust website as well. And I just want to say a big thank you to our funders. So that's Galloway Glens, Heritage Fund, DRAX and the D District Salmon Fishery Board. And also thanks to the University of Glasgow and Atlantic Salmon Trust, who's providing us with a lot of support through this project, and as well as the landowners as well that are also supporting this project.
That was brilliant, Sam. Thank you very much. Before we move on, we've got a couple of questions emanating from this, and maybe Sam and Ken would open up and answer them. But the one came I found quite interesting about standing water. Comment was from Gordon. There's no surname on it, so apologies, Gordon. Standing water query. He said that many historic lochs, salmon fisheries on lochs in Ireland and Scotland. With lots of, it was quite confusing. They had lots of standing water to pass through before they left the sea. So why the increase in mortality? Is that a long-standing thing, or is this a lack of adaptation to new lochs being put onto watercourses where formerly there weren't any? Sam, would you like to have a go at that?
Yeah, so I would say it's a bit of a combo of them both. So standing waters would have historically been there in some areas, but with the hydro schemes, often the water levels in the rivers can change quite dramatically, and that can have a big influence on whether the smolts can migrate through them or not. And even the reservoirs above the dams, like they don't have the natural flow that the smolts would normally follow. So yeah, I don't know, Ken, if you have anything to add to that in respect to islands as well.
Yeah, there's certainly very good evidence at this stage that once, as Sam was saying, once the flow rate drops off, whether it's in still water in terms of a loch or still water in terms of a very slow part of a river, smolts don't do as well in terms of migrating through. And consistently, the research is showing that they find passage through lochs more difficult than they do through flowing water. That's a combination of the water itself. Obviously, they're open to predation as well when they're in a situation where the flow rates are dropping. But you have to be very careful if you're putting migrating smolts, whether it's salmon or sea trout, through still water. Definitely a tendency for them to do much poorer in those sort of conditions.
Thank you. And there's another pertinent question querying the tagging, acoustic tagging. Maybe you'd like to do a very brief explanation, Sam, on how you place the tags into the fish and the process, and in fact you have to have certain qualifications and training to do this, don't you?
Yes, yeah. So everyone who's a tagger has a home office, like a personal home office license, and is trained up to scratch on how to do this process. There's a small incision made in the fish under anaesthetic, and a tag is inserted, and sutures are applied, and then we allow them to recover for a good length of time before releasing them back into the river.
That's brilliant. So the next phase of our project, our gathering event, is a little bit different to what we normally do. And Ken, Sam, and myself are going to have a little discussion around some little topic areas. So McNab is now going to start sharing slides for us. Thank you, McNab. And he's also going to be harvesting for questions in the comments section as well. But so we're going to start off with these sort of like meant to be provocative comments. Why salmon migrates is the first one, with the bullet points. Migration results in improved feeding. Considerable energy is expended making the journey back to the feeding destination and back to original stream. There's an increased, also an increased risk of predation and mortality from other causes. At the end of the day, whether to migrate or remain as a resident is a balance between benefits and gains, certain risk. So we'll maybe start off on that one, and I guess I'm going to start off with a very simple thing from my own experience of fisheries. Being big and fat is probably a bad trait for a human. But for many other animals that are producing lots of eggs, it's actually probably a pretty good trait. So the idea is to get as large as possible. It's a very simplistic terms to produce as many eggs as possible to have a greater opportunity to reproduce within the species. Ken, would you like to maybe move off on that one?
Yeah, I think the interesting one for me there was the one in relation to the energy that the fish expend. And there's a lot of work going on at the moment now by some very clever French modelers who are looking at this whole area of energetics. I remember many, many years ago, I had just joined the staff of the Marine Institute in Ireland, and we were very lucky to have over some oceanographers from NOAA in the States. And we had one guy who was particularly bright, and I was paired off with him to share ideas in terms of the projects we were undertaking. He knew absolutely nothing about Atlantic salmon, which is great because that means that you're going to get somebody who has a very, very clever mind and a very fresh brain. And he asked me to explain to him what was happening from the west coast of Ireland up to the feeding grounds in Norway. And he sat back and he just thought about this. And as a lot of these very deep thinking people do, he said very little, complete opposite to myself. And when I was finished, he just looked at me and he said, yeah, they ain't doing much swimming. Because when he realized that they were going out at about, as I said earlier, 12 or 15 centimeters, coming back at 60 centimeters in a little over a year's time, he realized very quickly that in order to gain that amount of energy, they really had to all the time be making advances in terms of their size. So this idea of having the fitter fish going out, the fish, as Nick was saying, that are bigger going out, the fish that can actually make the most of the energy that's available in the top layers of the ocean, that's a huge, huge advantage to a fish to be in a position where they can very quickly begin to actually put on the flesh that's required both to feed and also to grow and mature in order to come back.
Thanks, and remember as well, because the fat layers that they put on and the muscle mass they put on is then broken down in essence when they come back into the river. So the more of that they can gain themselves, they can break that down and produce it into egg mass just prior to spawning. Sam, would you like to continue on with that?
Yeah, so it's always good for the female to get bigger because she can have a lot more eggs. But then there's a trade-off in the female also, like does she have many small eggs or fewer large eggs? So there's this trade-off as well within the female. So for example, if the female has a good environment and many resources to choose from, she might choose to invest in many small eggs because the eggs are more likely to survive. Whereas in environments where they maybe have hardly any resources, she'll invest more in each individual egg so the eggs are larger. And that enables them larger size like we were talking about. There's more survivability there. So it gives her offspring a better chance to survive in these areas. And then you have cases where the conditions are just uncertain. So for example, in Iceland, the anadromous char up there, they have these very variable egg sizes because they don't have an idea of what the conditions are going to be like in the local spawning grounds. So they produce variable egg sizes as like a bet hedging strategy, but then for the offspring to give the best survival chances for her offspring. So there's that there's the growing large as a female, but also that decision of her local environment as well. It's important to consider.
That's very good, actually, there for you to bring in one of another salmon of the chart. Of course, in the waters around Britain and Ireland, we've got another very important salmon of the sea trout and the brown trout being essentially the same species. And of course, they have a similar sort of strategy in terms of choosing to go to sea or not to go to sea. But of course, they're a little bit more plastic, aren't they? But with almost all of the European salmon going to sea, some North American salmon don't. And where with the trout, there's a far bigger game going on here, isn't there? And the chances of what you choose to do. Ken, would you maybe like to expand on that a little bit?
Yeah, well, I'm really, as you know, I'm really keen on sea trout because I think they're the most fascinating creatures And certainly in the context of, I saw a point there that was raised in the chat earlier about this difference in proportions between male and female and the way it varies, because in sea trout, it's fairly consistent. Salmon, it can be a bit variable in that in the context of grills, sometimes you get a 50-50, almost invariably again, in terms of the bigger multi-sea winter salmon, as Sam was saying, it's mostly females that actually come back. But one thing that scientists are doing now, we've only learned how to do it over the last 5 or 6 years. We can use scales off little smolts that are going to sea now to see what sex they are. And what we're finding is some really quite extraordinary stuff, and some recent information that we got at a meeting about a week ago. One of the studies has shown that in going to sea, in some of the rivers that have been looked at, it is predominantly female smolts that are going to sea, as well as female adults that are coming back. We had almost assumed, I suppose, in the past that it was almost 50-50. So this balance between male, female, between what migrates and what stays, it's so delicate that in the context of all the changes that we're seeing that are related to pressures and related to climate change, it may very well be that there are much more subtle shifts going on than we may have allowed for in the past.
Yeah, going back to actually to some of the presentation stuff there as well, we start talking about these payoffs and the challenges the fish are taking and under the changing circumstances. There's been queries asked about sex ratios of different fish, and I suppose this pit sits with the sea trout and the salmon, but there's different sex ratios, isn't there, between different types, if you like. So in many sea trout populations, they are principally spawning with male brown trout, or just call them a resident trout. And also within the salmon population, there's a disproportionate relationship, isn't there, between multi-sea winter fish, grilse, and of course the ones we stay at home. Sam, would you like to maybe expand a little bit on that?
Yes, I think a lot of what we're seeing at the moment is there's a lot more grills that are coming back more than the multi-sea winter, fishes. Whether that's, I don't know if anyone has any input on that, or anyone in the chat can maybe talk about why that might be happening. Or
certainly, Nick and Sam, certainly there's also this amazing balance between genes and environment. And the geneticists now talk about switch genes, about genes that can actually be switched on or switched off by these pressures and by changes in these pressures. So we're fortunate in a way in that we are seeing the adaptation that I talked about in my talk, albeit at a very local level in terms of individual fish. But the other thing that's very important to remember as well is that nothing is very simple in this fish world. And when two fish spawn, we often assume, as we saw on the video there, that predominantly it's a big male and a big female. But as Sam mentioned earlier as well, in terms of these little precocious males, certainly one of the reds that we looked at had 8 individual fish contributing to that one red. And the importance of the genes that are coming in from those little resident males should not be underestimated. Because if you have a situation where a population is really under pressure, one way that nature has of making absolutely certain that genetically the gene pool is kept healthy is by these little resident males. And it may very well be that some of these males don't go to sea at all, the little salmon males. They may very well be there for one purpose and one purpose alone, and that's to keep the genes healthy within the population.
There's a very good points coming there, actually, in the chat section from Martin Schofield about the in very, very threatened rivers, in the absence of male salmon, the female will, of course, attempt to spawn, and the precocious part will still go in there, wouldn't they? And do the job of fertilization. So it's a fantastic safety valve that we have for the species.
Well, we had some amazing examples of that, albeit tragically, in Ireland in the past when we had our infamous driftnet fishery going. There was a time when the southern rivers in Ireland, these are big, big rivers, they're as big as the sort of spey type size rivers in the south, and they used to hold very large numbers of multi-sea winter fish. And my colleague, when the drift nets were at their peak and we were losing over 90% of our fish to the drift nets, he went and did a big survey on a river called the River Suir, which is one of the most productive rivers in the country. As well as being big, it's on limestone, so it produces huge numbers of fish. And he found vast numbers of salmon parr. in a situation where the anglers were catching very, very few fish. And he got the flu, and I was dispatched down to a huge meeting in County Cork to explain to anglers that we weren't going to build a hatchery because there was loads of small wild parr in the river. And they wouldn't believe me. And I was hunted out of the room eventually at the end of the talk, and that's no exaggeration. But it does show exactly that point, that if you have a good abundance of these little male parr, and even as a modest proportion of females coming back in, the stock dynamics of the salmon population is such that it will fill all the gaps that are there. Genetically, it's a hugely dangerous game, but biologically, it's a great way of keeping the rivers full of small fish.
Yeah, I think we'll move on to the next slide. But I think it's a case I've found in my career in fisheries is that lots of people think the river's empty of fish, and often it's surprisingly full of fish. But just because you're not seeing them, it doesn't always relate to adult fish coming back very well, and those relationships are quite difficult to sometimes understand. So getting the balance just right. An individual has no way of assessing this directly, but its decision is informed by its genes. We've discussed some of this. Overall, genes and environmental factors contribute about equally to the variability of migration versus residency in trout. I guess we've covered a number of these slides already, but I guess it's referring maybe back to your switch genes type of thing, where the slide, there's lots of potential within the fish, and having that huge diversity within the population gives a greater opportunity for the fish to adapt and change to environmental change, which particularly as environmental change is now far more rapid than it's ever been. Sam, would you like to take off on that?
Yeah, I mean, we touched upon the importance of plasticity earlier in respect to buffering against climate change. So for those who don't know what plasticity is, it's when a single genotype can respond by producing different phenotypes to different environmental conditions. But what we don't understand, so for example, the smolts that we spoke about, advancing their migration 2.5 days earlier, that is great. It shows a plastic response to the environment, but what about is the underlying genetic basis that ultimately might depend on whether and how a smolt or an adult migrator can respond to changing environmental conditions. So for example, if a migratory phenotype, so an earlier migratory phenotype, has a simple genetic basis, any integration, poor integration from things like farmed escapees or small effective population size where genetic drift might come into play and lose this genetic variation that might associate to an earlier migratory phenotype, then perhaps that lost. And that's what's been found in Pacific salmon. A couple of species of Pacific salmon have this large effect locus that has evolved independently for earlier migratory phenotype. So if that variation at that locus is lost, then does that mean the earlier migratory phenotype is lost? We just don't know if plasticity is enough to buffer against environmental change, and we need to really have a better understanding of the underlying genetic architecture to really know how these populations are going to be able to respond to the climate change, and whether they're able to change their migration based on that, or whether they're going to lose that genetic variation and not unable to change. So it's really that it's not genes, nature or nurture, it's a bit of a combination of the both. Like it's the interplay between the two that's really important.
I suppose one of the more terrifying things about climate change is this plasticity is built into these species and into many species for a normal variable climate, because the climate has varied forever. And we've seen ups and downs in salmon populations over the recorded records. Some records go back a couple of hundred years, but they've never been subjected to such a rapid environmental change, have they, Ken?
No, I don't think so. I don't think so. Nick, while I remember, I should really do what we were supposed to do at the beginning and just pay credit to Professor Andy Ferguson. A lot of the bullets that we have here were actually taken from some of the material that Andy produces. And if any of you get an opportunity either to read any of Andy's scientific articles or books, or indeed his popular articles, because he's also a very keen angler, he's an absolute genius in relation to this area of the balance, if you like, between genetics and environment. So just to mention that, because we do all of us owe a lot of credit to Andy in terms of getting us thinking along these directions. I also see from Richard a very interesting point coming in, and it's the whole question of whether or not the changes that we're talking about, are they locked into the bodies of the fish in any way that we can tell that there are changes happening? And he asks about othalates, about the ear stones of fish. And we have a very interesting project just kicking off now in AST, where we're looking at the ear stones of fish, but we're also looking at the eyeballs of fish. So we've had trust staff and board staff all over the winter collecting the heads of salmon that have died after spawning, so that we could collect the eyes. And as I say, we're also looking at the ear stones. And the reason for that is that chemically, within those particular items, within the eyes and within the ear stones, there are isotopes. There are different forms of elements like oxygen and so on. And the actual ratios of these isotopes can, we hope, actually tell us something about where the fish may have been feeding at sea, and also may tell us something about the changes that are happening in the chemistry and the surface layers of the ocean. So there's all sorts of new science actually opening up for us in terms of being able to trace not alone what is happening, but the most important part, why is it happening? And that really is the key in terms of understanding these changes and why these switches are happening. Why is it, as Sam said earlier, that the grilse are becoming more dominant and the multi-sea winter fish are not as dominant? And it may very well be that we're getting grilse back now that are multi-sea winter fish in grilse clothing. They may be fish that are at sea where normally all of the cues that are in their body would tell them to stay at sea for 2 or 3 years. But because of the fact that maybe food is scarce, or perhaps the temperature has changed, suddenly the switch just gently goes over in the other direction. And they say, look, my main job is to reproduce. I'm going back into the river now. I'm not going to chance staying in this very uncomfortable environment for another 2 years. I might die. And they hightail it back as grills. So that's the way these things can be switched by environmental factors.
Okay, we'll move on to the next points. And actually, well said about Professor Ferguson. Was my mistake. I should have actually introduced it at that point. So thank you. But the next slide is where to go. The next decision is where to migrate to. Migration destination is largely determined by an individual's genes based upon the past experience of its ancestors, as influenced by natural selection. In many cases, the advantages and disadvantages of migration are likely to be on a knife edge, and it takes very little to tip the balance in favour of not migrating or migrating to a different habitat. And I guess, Ken, that kind of relates back to your last point there, where all these decisions are on a knife edge, and very subtle changes in the environment can make a big change in the behaviour of the fish.
Yeah, it certainly can. And again, going back to my favorite species, back to the sea trout, you can see this happening in sea trout quite suddenly. And certainly in the past, when myself and Andy Walker, when we were really fighting the good fight in the 90s in terms of the first real problems that we had with sea lice, it was very obvious at that stage that the behavior of the sea trout, it changed fundamentally as a consequence of those very immediate impacts from the sea lice. And these early returning sea trout smolts that I was unfortunate enough to be the first one to find in 1989, would you believe? But those fish coming back in, their pattern of migration was being changed by a parasite, but still it was an environmental factor, albeit that it was man-made. So these particular changes can happen, and they can happen very fast. And we need to be aware of that. If I've learned one lesson in terms of the loss of sea trout stocks that I've seen off the west coast of Scotland and Ireland, is don't take any of these things for granted. Do not take them for granted. They can disappear in the blink of an eye. And I couldn't believe how quickly some of our premier sea trout stocks disappeared, and we still don't have them back. So we have to be very vigilant in terms of making sure that any of the pressures that Sam talked about earlier, that we really are determined in minimizing these at a time when our salmon and sea trout stocks are under pressure.
As a well put warning, I too worked with Andy briefly in the very early 90s, 1991, I think it was, on the Loch Maree system. Loch Maree was the predominant sea trout loch, probably in the world, to many people would say. And we were still catching sea trout there for samples, but they were all very early returning finnock. But they're pretty much going to sea and almost turning around straight away. and the lice loadings were immense, and the population couldn't stand it. And until we resolve that sea lice issue, sea trout are effectively a dysfunctional fish in many of these areas, which is a great, I personally think it's a crime, actually. Sam, would you like to come into these sort of subtle changes in environment and how they may just sort of change things about from your experience?
Well, again, I just always go back to the plasticity side of things. I think that's really important for buffering against changes in the environment to a certain point. And yeah, I think Ken just kind of covered the points with that. We need to appreciate what we have in these river systems at the moment and try and improve what we can too. If everyone makes improvements to their local river systems, then perhaps we can retain some of these species for a lot longer. That might be coming up sooner than we hope it to.
Okay, winning or losing. So we're discussing the knife edge side of this. In many cases, the advantages and disadvantages of migration are likely on a knife edge. It takes very little to tip the balance in favour of not migrating or migrating to a different habitat. Plastic life histories, multiple sea ages, residency and feeding grounds, and bet hedging. We're talking about bet hedging strategies here, such as egg size, fecundity, body size, adaptations to prevailing environmental conditions and buffering against climate change. We'll also discuss integration with farmed escapees. Now, we've discussed some of these stuff already in this wider discussion, but Sam, you were talking about the egg size variation. Is that that's something that's present in many salmonid species, isn't it? It's not just within, and it can have a big bearing on what the fish may become.
Yes, yeah. A lot of salmonids are very plastic in their life histories, especially in egg sizes. So for my PhD, I looked a lot at whether different size eggs can produce a different phenotype of fish. So in Arctic char, you have different kind of a benthic phenotype or more pelagic phenotype. And we asked the question of whether a certain egg size can produce a fish with a certain phenotype, which is very subtle changes. There are very subtle changes and associated levels of gene expression changes as well. And that will also be the case in other salmonids. Like more and more studies are being published showing how egg size can actually change the phenotype of offspring. And then they have this developmental plasticity with the gene expression and the exposure to different prey types that may actually encourage a different phenotype. So that can create this initial diversity that may be needed to cope with changes in their environments. So some fish might survive, some fish might not, depending on the phenotype that they get exposed to.
Ken, would you like to come in on that?
Yeah, there's an added point as well, and it's something that myself and a couple of colleagues of mine did a lot of work on in the 90s, and that's the whole question, again, back to my favorite species, back to sea trout. The whole question in terms of trout and sea trout is, which of the year classes are laying these big eggs, and which are the ones that you have to conserve? So we did a lot of work on the west coast of Ireland, where the sea trout are quite small. But what we found was that the majority of the eggs were being laid by 2 year classes of sea trout. And we tried to introduce slot limits because the anglers all had size limits. So what they were doing was putting back the finnock, and they were killing the very fish that were laying the eggs. And we tried to introduce slot limits, and we failed miserably because the anglers just couldn't get it across, just couldn't get it into their head that a lot of the finnock may very well not spawn successfully. A lot of them may die over winter. And if you want to have a nice, fresh little finnock on the pan, that's the one to have as a breakfast trout. But don't be killing the trout, in our case, of 1.25 pounds and 1.5 pounds. And if you want to kill a very big fish, that's fine. Because when we looked at the big sea trout, we found that quite a lot of the big males, where there were males present, after 2 or 3 spawnings, the sperm count fell. So if you want to have a big trophy male sea trout up on the wall, that's fine. Or if you want to have a little finnock on a pan to eat, that's fine. But the fish you have to conserve are the ones that are giving you these big eggs and producing most of the fish. So it ties in exactly with what Sam was saying. But from an angling point of view, difficult to get that across because traditionally we think of small fish as being delicate and the bigger fish being the fish to take home.
Yeah, something from my career, I remember actually asking about putting slot limits onto the river for brown trout. And actually, the angling club that started off decided it was far too complicated. We just went for complete catch and release, which worked pretty well as well. But we'll go back to maybe a couple of comments in the chat room that I'm going to just bring out, which is slightly different to this, and then we'll wrap up because I've got a beer getting nice and cold, and I'd like to visit it fairly soon. So there's a comment here on predation and predation going through the locks. Now, Sam, with the work you're doing, we may pick up on some of that, won't we? With we're going to be putting, I can't remember how many tags it is into the smolts, or you're going to be doing it. And of course, those fish are going to get challenged by a number of things, not just the lack of access at certain water flows past barriers, but they're also going to get challenged by pike, by perch, by maybe avian predators. So we may pick up some ideas on predatory impacts as well, won't we?
Yeah, I mean, the tags that we're using, we won't be able to detect whether they've been eaten by a predator as such, because you can get some tags which have this dissolvable membrane. So when the fish gets predated upon and it goes inside the stomach, their stomach acids will actually dissolve the outer membrane of the tag, and it will send you. So when you download the data from the receiver, if you're getting these pings, then that actual pattern could be from the predator. So that dissolvable membrane around the tag will tell you that it's a predator, not your salmon. So we don't actually have those fancy tags. We're going to try and just hopefully try and distinguish between predation or not, depending on the movement patterns, and look into general movement patterns of salmon to try and find that pattern out.
Yeah, many years ago I did some radio tracking work in the early days of tracking fish, and we found otter predation was quite easy to predict from some of the salmon who were predated, mainly because the salmon disappeared 30 meters up the bank and would find the little tag sitting in the middle of the carcass. The otter would be eaten all the way around the salmon, but left the tag in the perfect location where I put it just 2 weeks earlier. Yeah. So I think we're going to be closing this event up very, very shortly. And I would like to thank very much former colleagues of mine actually for attending, and particularly though to Ken and Sam, who I know how much work it takes to put these presentations together. The work that Galloway Glens is doing with Galloway Fisheries Trust, we're providing the money, and it's up to Galloway Fisheries Trust to manage the rest of it. But I'm really excited by it. It's a really interesting project, and using the acoustic tags is something slightly different to what their traditional use has been. And so we're really up for this, and we'll report back in Galloway Glens on a regular basis with Sam. Maybe some little videos and things like that of the work that's been going on. So without further ado, what I'd like everyone to do is at this point unmute themselves. And the traditional way to end a meeting is to give a round of applause to the people who've put all the work in to present the evening. So thank you very much, Ken, and thank you very much, Sam. Thank you very much.